Let's delve into the next topic on satellite image time series. In this segment, we explore the fascinating concept of satellite image time series, which provides us with a time-lapse view of our planet's transformations. This remarkable capability is achieved through the synergy of satellites and advanced computing. Now, let's look at a practical example of how satellite image time series can be used. Here, we have satellite images that display land use and land cover changes in Islamabad Capital Territory from 1976 to 2016. These visuals give us a spatio-temporal view of urban sprawl assessment. This table depicts the changes in various land cover classes throughout the years. Let's break down the changes in land cover classes for a clearer understanding. Tree canopy is greater than 40% in the forest. In 1976, this area covered 182.87 square kilometers. Over time, it decreased to 132.27 square kilometers by 2016. This signifies a reduction in dense forested areas with a canopy cover of over 40%. Also, the SDG shift was 0.62 from 1976 to 2000 and increased to 1.36 from 2000 to 2016. Now, we'll highlight the compelling advantages of satellite image time series. These advantages are derived from long-term satellite data, improved computing power, and cloud computing resources, which collectively empower us to efficiently detect and understand changes on Earth. This technology is invaluable in various scenarios, including emergency response during natural disasters and promoting positive changes worldwide. Now, let's look at a real-world example. In August 2023, Hawaii faced devastating wildfires. The color infrared imagery from ESA Copernicus Sentinel-2 satellite overpasses illustrates Lahaina, Maui, before and after the wildfires. It vividly displays areas that were burned in dark green and brown, while red areas signify healthy vegetation. These images and data played a critical role in assessing the impact of the wildfires, aiding emergency responders and informing recovery efforts. So, the next slide is on time series analysis and its types. In geospatial technology, we have the capability to study Earth's changes over time in diverse ways, much like observing the transition of seasons or tracking sudden events. Let's dive into the different types of time series analysis. Annual versus seasonal trends. Seasonal trends. These trends are influenced by the changing seasons, impacting various environmental factors. Seasonal trends often relate to vegetation, the growth and decline of vegetation, which is influenced by factors like temperature, sunlight, and precipitation. Temperature. Seasonal temperature changes can have a significant impact on the environment. Snow cover. In regions where snowfall occurs, you can track the extent and duration of snow cover. This is crucial for understanding the water cycle and its influence on ecosystems. Precipitation. Seasonal variations in precipitation, such as rainy seasons and dry seasons, play a vital role in shaping the environment. Monitoring these trends is crucial for agriculture and water resource management. The GIF displays the seasonal shift in the vegetation cover of Pakistan, showcasing the dynamic nature of the environment. Annual trends. In contrast to seasonal trends, which occur within a year, annual trends cover longer time periods, typically spanning several years. These trends involve land cover, land use, monitoring changes in land cover and land use practices over time. For instance, the transformation of a forested area into urban development or agricultural land. LAI, or Leaf Area Index. This metric quantifies the amount of leaf canopy in an area. Annual trends in LAI can reveal how vegetation changes in density and distribution. The image shows the Leaf Area Index of South Asia, highlighting how we can quantitatively measure the canopy's growth over time. NDVI, or Normalized Difference Vegetation Index. NDVI measures the greenness of an area, providing insights into vegetation health. Annual trends in NDVI can highlight shifts in ecosystem dynamics. Alright, next, we have gradual and abrupt types of changes. In geospatial analysis, we encounter a wide range of changes in our environment. Understanding these changes, whether they happen gradually over time or suddenly, is essential for effective monitoring and management. Let's delve into the distinctions between gradual and abrupt changes. Gradual changes develop over an extended period, often involving a slow transformation of environmental elements. Some examples include insect infestation in forests. Gradual changes in forests often involve insect infestations. These infestations can weaken or kill trees over an extended period, impacting the overall forest health. Land degradation. Land degradation is a slow, ongoing process where the quality of soil and land declines over time due to factors like erosion, deforestation, or overuse. It can have long-term impacts on agricultural productivity. Forest recovery. After disturbances like logging, forest fires, or land clearing, gradual changes can be observed in forest ecosystems as they recover over years or even decades. This involves the re-establishment of plant and animal communities. Abrupt changes are sudden and often disruptive events that can significantly alter the environment in a short period. Here are some examples. Wildfires. Wildfires are sudden, catastrophic events that result in the rapid and extensive burning of vegetation. They can cause significant damage to ecosystems and communities in a short period with long-lasting effects. Deforestation. Abrupt changes in land cover occur with deforestation. Large areas of forest are rapidly cleared, often for agriculture, urbanization, or infrastructure development, leading to a sudden and dramatic loss of forested land. Natural disasters. Events like earthquakes, hurricanes, floods, and tsunamis are abrupt changes that can have immediate, devastating impacts on the environment and human settlements. They often require rapid response and recovery efforts. This graph here displays the NDVI changes in the aftermath of a forest fire in Margala Hills. NDVI values range from -1 to 1, with higher values indicating healthy vegetation. In this section, you can see a great fall in NDVI value. This is the phase of the forest fire, an example of an abrupt change, where the NDVI values have significantly decreased, showing the impact of the fire on the vegetation cover. Okay, so another way we study Earth's changes is by examining anomalies. Anomalies are essentially variations from the long-term average, and they play a vital role in understanding our environment. They help us identify deviations from what's considered normal and can be valuable for detecting unusual events or trends. One excellent example of this is the FAO Global NDVI Anomalies. NDVI, or Normalized Difference Vegetation Index, is a measure of vegetation health. By calculating anomalies in NDVI, we can detect areas where vegetation growth is significantly different from the long-term average.